Embark on a fascinating journey beyond our imagination. On August 23, 2023, India etched its name in lunar history with the Chandrayaan-3 mission. What secrets do the footprints on the moon hold? And what more can the cold lunar silence reveal to us? Challenges of landing. The selection of the lunar South Pole as the landing site for Chandrayaan-3 was driven by the quest for unique and essential discoveries for lunar understanding. Despite significant challenges, this region promised to unveil unexplored aspects of the moon. Its rugged terrain, characterized by large craters and steep slopes, posed difficulties in finding a safe and controlled landing spot. Perpetual darkness in some areas, resulting from the lunar axial tilt, raised energy concerns as limited sunlight made it challenging to power the necessary solar panels for the mission. Additionally, extreme temperatures at the South Pole, reaching 230 degrees Celsius during the lunar night, raised concerns about the integrity of electronic components. The design of Chandrayaan-3, with a planned duration of 2 weeks, aimed to confront these challenges. Despite these obstacles, the successful landing opened the door to a deeper understanding of the lunar atmosphere, plasma density, and thermal variations on the surface. Chandrayaan-3, overcoming these adversities, provides valuable data on lunar habitability and marks a crucial step toward future explorations of the lunar South Pole and its scientific mysteries. The strategic choice of this landing site underscores the determination of space exploration to unravel the deepest secrets of our natural satellite. Lunar atmosphere and plasma density. The revelation of the lunar atmosphere through Chandrayaan-3 marks a milestone in space exploration. Although extremely tenuous, the lunar exosphere has a pressure of approximately 0.3 nanopascals, a minute fraction compared to Earth's atmosphere. Plasma density measurements conducted by Chandrayaan-3 at the lunar South Pole revealed densities ranging between 5 and 30 million electrons per cubic meter, crucial data for understanding atmospheric conditions in this region. This information has direct implications for radio communications in future lunar missions, as plasma density affects signal speed. The higher the density, the slower the data transmission. This knowledge is essential for optimizing communications and navigation during upcoming lunar explorations. By providing these data, Chandrayaan-3 significantly contributes to the planning and execution of future space missions, marking a crucial advancement in our understanding of the lunar atmosphere and its practical implications for sustainable space exploration. Lunar temperature. Chandrayaan-3's exploration of lunar temperature has unveiled remarkable extremes on the lunar surface. With daytime temperatures reaching around 60 degrees Celsius, 140 degrees Celsius on the lunar surface, there is a drastic drop to 10 degrees Celsius, 14 degrees Celsius, just 8 centimeters below the surface. This phenomenon indicates that the upper lunar soil functions as an efficient thermal insulator. This thermal variation has significant implications for future missions and the possibility of constructing lunar habitats. Chandrayaan-3 has provided essential data to understand thermal conditions on the moon, crucial information for designing life support systems and structures that shield astronauts from extreme temperature fluctuations. The lunar soil's ability to act as a thermal insulator opens promising prospects for future lunar habitability, offering innovative solutions to mitigate the extreme conditions of the lunar environment. These discoveries contribute significantly to our understanding of the moon as a destination for human exploration and underscore the importance of considering not only the lunar surface, but also the thermal conditions beneath it in mission planning and lunar infrastructure construction. Possible lunar earthquake. Chandrayaan-3, after its historic lunar landing, surprised the scientific community by recording a possible lunar earthquake just 3 days after touchdown. The Instrument for Lunar Seismic Activity, ILSA, detected this unique phenomenon, triggering questions about its causes. Lunar earthquakes can originate from cosmic impacts, terrestrial and solar tidal forces, or extreme thermal variations. This event, the first recorded in over half a century, stands as a unique opportunity to understand the lunar internal dynamics. Investigating this earthquake not only broadens our perspective on seismic activity on the moon, but could also reveal valuable information about lunar evolution and its internal processes. Chandrayaan-3, by capturing this unusual event, becomes an essential tool to advance our understanding of lunar seismic phenomena. What secrets will this mysterious earthquake hide about lunar internal activity? And how will it influence future lunar exploration missions? As we unravel this enigma, Chandrayaan-3 emerges as a pioneer in lunar research, providing key data to expand our knowledge of the Moon and its still poorly understood seismic phenomena. Discovery of sulfur. The laser-induced breakdown spectrometer of rover Pagon on the Chandrayaan-3 mission has unveiled intriguing discoveries, highlighting the surprising element: sulfur. While analyzing lunar composition, the spectrometer identified not only common elements like aluminum, calcium, and titanium, but also the notable presence of sulfur. This surprising find has significant implications for understanding lunar geology. Sulfur, commonly associated with volcanic activity, could indicate unique geological processes on the Moon. Its presence is crucial for unraveling lunar history, as it relates to phenomena such as the breakdown of water ice due to high-energy radiation. This phenomenon could have released sulfur and other elements, providing a new layer of information about lunar evolution. Interestingly, no orbiter crossing the lunar South Pole had previously detected sulfur, making this discovery even more intriguing. The cold trapping theory suggests that in extremely cold and shaded regions of polar craters, water vapor can turn into ice, trapping additional molecules like sulfur. This process might have been triggered by lunar radiation. Detailed analysis of sulfur raises new questions about the geological history of the Moon and its relationship with lunar water. This discovery underscores the complexity and richness of lunar composition, challenging our previous perceptions. Chandrayaan-3, by unveiling the presence of sulfur, not only advances lunar scientific exploration, but also raises exciting questions about the geological processes that have shaped our natural satellite. Where is water ice? In contrast to previous findings of water ice on the Moon, Chandrayaan-3 failed to find direct evidence of this crucial resource. In 2008, the Moon Mineralogy Mapper, M3, on India's Chandrayaan-1 mission, detected absorption features associated with molecules containing hydroxyl or water in lunar polar regions. However, despite thorough analyses, Chandrayaan-3's rover Pagon did not find clear evidence of water ice on the lunar surface. This discrepancy raises two possible explanations. The first suggests that the Pragyan rover might not have been in the right location at the right time. The 2018 study confirming the presence of water ice indicated that these deposits were evenly distributed at the lunar South Pole, primarily concentrated in craters. Chandrayaan-3 may have landed in a region without the presence of water ice, as these deposits appear to be specific to certain lunar areas. The second explanation comes from Chandrayaan-3's own discovery: the temperature probe on the VCAM chassis. This probe recorded a significant temperature drop just below the lunar surface, indicating that lunar soil is a poor heat conductor. This phenomenon suggests that water ice could be present beneath the surface, not in the upper layer. Chandrayaan-3 might not have found direct evidence of water ice on the surface, but the data indicate the possibility of its presence in deeper layers. Mission duration and success. The carefully planned Chandrayaan-3 mission had an intended duration of 2 Earth weeks, equivalent to 1 lunar day of sunlight. This time constraint was due to various challenges at the lunar South Pole, such as rugged terrain, perpetual darkness, and extreme temperatures. Chandrayaan-3 faced adverse conditions. To ensure a safe and controlled landing in a lunar region known for its mountainous topography and challenging weather. Despite these obstacles, the mission was deemed successful in achieving its primary goal: a soft landing on the Moon. Chandrayaan-3 excelled in overcoming the inherent difficulties at the lunar South Pole and gathered a significant amount of valuable data during its brief period of activity. The complexity of the terrain, prolonged darkness, and extreme temperatures in the region did not prevent the Indian spacecraft from reaching its crucial objective. Over the 2 weeks of lunar activity, it made key discoveries, from unveiling the lunar atmosphere to detailed measurements of plasma density and analysis of elements on the lunar surface. Each step of this mission contributed not only to understanding the Moon, but also to expanding our knowledge of lunar phenomena. Although Chandrayaan-3 couldn't find direct evidence of water ice on the lunar surface, Its findings and challenges underscore the importance of exploring the lunar South Pole, a resource-rich region. The success of this mission lays the groundwork for future explorations, including Chandrayaan-4, which will embark on a collaboration with Japan to extensively explore the lunar South Pole. Chandrayaan-3, by fulfilling its primary mission, opens the door to an exciting chapter in lunar exploration and continues to inspire the scientific community and space exploration enthusiasts worldwide. If you enjoyed the video, don't forget to subscribe.